Okay, this is the example video for the example calculations for energy and work located on the energy and work page on the class website. So there are 4 problems. I encourage you to read along with the problems first and then watch the video. So here we go. This is number 1. Question reads, a force of 20 newtons pushes a box for a distance of 4 meters. How much work is done? All right, so we always start. Let's write the givens. We're told that a force of 20 newtons pushes a box for a distance of 4 meters. Here I'm using delta x to denote the distance like we usually do. How much work is done? Well, the definition of work in physics, work equals force times distance. And sometimes that's written work equals FD. Some textbooks use D, some use delta x. So just don't be confused, they mean the same thing. Force times the distance through which it is applied. And so if work equals force times distance, then a force of 20 newtons applied for a distance of 4 meters. Now let's be very careful about our units here because this is a new unit. Equals 80 Newton meters. Now I just want to be clear. So we're going to split up our Newton into its definition. Kilogram meters per second squared times a meter, which gives us 80 kilogram meters squared per second squared. So the answer is 80 joules. Remember that the definition of the unit, energy and work, are both measured, among other units, in joules. We're going to use joules here. Remember the definition, 1 joule is defined to be 1 kilogram meter squared per second squared. So a Newton times a meter gives you that, and a number of other combinations of quantities will give you that. And when you see this combination of units, kilograms, meters squared per second squared, then you have joules. And that is either a work or an energy or both. Problem 2. How much work is done lifting a 10 kilogram rock 2 meters? Well, given the mass of our rock is 10 kilograms, and you lift it a distance or to a height, delta x is 2 meters, or sometimes you can see that listed as a height or a change in height. So just look out for whether or not sometimes things say h or delta h for the change in height. Okay? But again, work is force times distance. So now you have to ask yourself, how much force is required to move that rock, to lift it? Well, you're going to have to move its weight. You need to apply a force equal to its weight to lift it. So in this case, we're going to have our weight times the height. So just be aware that when you're doing work by lifting an object, you have to use its weight as the force, and the distance is going to be the height through which you lift it. Now weight, you know, is mg, and the height is going to be either h or d or delta x or whatever you like. How about we use delta x here? And so we have 10 kilograms times g, which is 9.8 meters per second squared. And you're going to lift it a height of 2 meters. So we have 10 times 9.8 times 2. So we get 196. Unit-wise, across the top in the numerator, we have kilograms times meters over second squared, which gives us a work of 196 joules. Kilograms, meters squared per second squared, joules. Number 3. A 2-kilogram rock is thrown at a velocity of 4 meters per second. What is its kinetic energy? So one of the things we talk about as a form of energy is kinetic energy, which is energy of motion. Okay? Kinetic energy is the energy that objects have when they're in motion in some coordinate system. Remember, motion is relative, so in some coordinate systems, or depending on your motion, you might determine a thing to have no kinetic energy relative to you. We're going to assume we're looking at this rock moving from a position of rest, so it's moving relative to us at rest. In any case, given the mass is 2 kilograms, the velocity is 4 meters per second. Find the kinetic energy. Now remember that kinetic energy, KE, is defined to be 1/2 times the mass times the square of the velocity. So let's do it. Kinetic energy, 1/2 times the mass times the velocity squared. Use your order of operations and all your math stuff. How about we do order of ops? 1/2, 2 kilograms. When you square the velocity, don't forget to square the units. 16 meters squared over second squared. Alrighty. So we have 2 over 2 for 1, so we get 16. Now unit-wise, the numerator, kilograms, meter squared over second squared. There it is, the definition of the joule. So this thing has kinetic energy of 16 joules. And the last example, number 4. A 10-kilogram rock is suspended in the air at a height of 2 meters. How much gravitational potential energy does it have? So another form of energy that we learn about here is called gravitational potential energy, which is the energy stored in the object's position relative to its height above the ground. The important thing to remember about potential energy, gravitational potential energy, is that it took some work to get the thing up there in the first place. That energy then becomes stored as potential. It has the potential to do some work or to get the object moving if you just let go and let it fall, etc. And we'll see more examples of that and discuss that. Given the mass is 10 kilograms, the height is 2 meters. Now the definition of gravitational potential energy, GPE, is mgh. The mass times the acceleration due to gravity times the height at which it is suspended above either the ground or the surface that it would fall onto if you let it fall. So we have 10 kilograms times 9.8 meters per second squared times 2 meters. 10 times 9.8 times 2 for 196. Look at our units across the top. Numerator, kilogram, meters, all over second squared. Kilogram meters squared per second squared for a GPE, gravitational potential energy, of 196 joules. Now that's interesting. If we go back and look at number 2, the amount of work to lift a 10 kilogram rock 2 meters was equal to force times distance. That's its weight times its height, and that's mgh. Lo and behold, when we look at the potential energy stored in that thing's position later, a 10 kilogram rock sitting at 2 meters above the ground or some other surface onto which it would fall, it has 196 joules of potential energy. So this is an excellent example of where, in this case, work to lift the rock becomes stored as gravitational potential energy that you can get back later by, I guess, letting go and letting it fall. Then that energy can be used to do work later too. If you let it fall on a nail and let it do some work, hammering a nail into a piece of wood or something, then it would do that many joules of work. So this was example calculations for energy and work, set 1.